Hello, this video is for Math 3 Unit 1 and it's focusing on shifts of functions. Now shifts of functions have been mentioned in the two previous courses. This standard is a standard for all three courses, Math 1, Math 2, and Math 3. But for the first semester of Math 3, this standard really takes center stage and we're going to learn many more functions and see how these shifts affect their graphs. And so this unit is a unit where we want students to really consolidate their understanding and to be able to generalize what they've learned about lines, exponentials, absolute values, and quadratic graphs to see that it is a general rule for all functions that this is how they behave. And so this is a summary of the shifts that they have learned, and it would be a nice summary thing to give your students eventually, but I think it is a beautiful place for discovery. If they haven't had a discovery moment before about shifts, then pulling out a graphing calculator or your Desmos on your computer or your tablet or your phone and just graphing a few functions for them, having them start to predict what they think will happen. And I know in the old Algebra 2 book there was a really nice exploration that most people didn't do on graphing absolute values because that wasn't really a topic that was covered in the initiative materials. And it's just a one-page or maybe a two-page thing which gives a lot of different possible things you might graph to have them discover it. So what there's a whole video on using Desmos, and so I'm going to save some of those comments from there, but I might graph a graph like f of x equals or y equals x squared, and then I might graph a graph like y equals x squared plus 3, have them observe what happened, then have them maybe predict what will happen if I graph y equals x squared minus 4, and they'll start to realize that that number you're adding on is just shifting things up and down. You then might be able to bring them back to, you remember when we did that with parabolas, you remember when we did that with lines, and so this is a generalized rule. I made a poster and put this on my wall so it was in front of them like every day except for test days for most of the first semester because we use this so much. And then you might want to move to exploring if there's a number inside parentheses, and this would relate to what they learned a little bit about vertex form in Math 2. And so that would be, if you started with this graph, what happens if you have an x minus 1 in here? I love it that most kids think they know this game by now, and they're pretty sure that maybe this will go backwards and forwards, which they're right, but it goes in the opposite direction of what they think. So if this is a negative 1 in here, then you will see it move to the right instead of the left as they'll predict. And if it's a positive that you put in here, then they will see it move to the left. And so it's a little opposite of what they predict. So those are some things you might be able to just graph on a graphing calculator or Desmos and have the students be able to experience that tiny piece of discovery. And then the reflections happen when the negative sign is put in front of the function. So for example, if you were doing this function, then maybe if you threw a negative sign in front of that, you would see the parabola suddenly was upside down instead of right side up. They might remember that and be able to predict that pretty well. And so the reason that happens, because these two things, students will get muddled in their head. Which one's across the x? Which one's across the y? The reason that happens is really because this right here is just another way of saying y. And so what we're doing when we put a negative in front of it is we're multiplying all the y values by a negative number. And so this is saying negative y's or opposite y's, and so all the y's are going to change signs. If they were all positive, like they were in this graph, then all the y's will become negative. If they were all negative, then all the y's will become positive. And so that's why this reflects across the x-axis, because the sign is being changed on every y value of every point. And so that's why that happens. And then this next one is what happens if the negative is inside. And now we should think about, well, the y value isn't having its sign changed. Really, the x value is having its sign changed because we're changing inside the number we plug in. And if you try to use this as an example, it's just not a very good example because it's just when we square a negative, it's going to come out positive, and so they won't really see much if you do that. You might prefer to use a different function that doesn't have something that would make make life positive, you could say, what if I used y equals 2x plus 1, and then y equals negative 2x plus 1, and see what happens to that graph. And what you should notice is that I come along with my 1 and I plug that in. In the original function, if I plugged 1 in, I would have gotten 2 plus 1 is 3, but now when I plug the 1 in, I'm going to change the value, and so it's going to act like a negative 1. It will give me the y value that negative 1 would have given me if I plugged in there. So consequently that reflects across the y-axis. Alright, so given those shifts, and once you have the kids with these as a kind of summary statement, which you've got them to that spot. I did this in day 2 of this unit. Day 1, I just had them graph lines like they'd already learned how to graph lines, but really what we don't want is for them to just plot points all the way through this unit. We want them to start realizing that shifts are something you can capitalize on to make graphs. And so let me just show you a few problems that you can do that. And so worksheet 1 on the back is a first place where we talk a little bit about the shifts. So you might want to have mentioned it during your talk on that time as you're reviewing lines. Because the notation here, instead of being just y equals, is definitely shift notation. Here's our original function, and here is our function with 4 added. And we know that when we're adding this 4, basically we're taking all the y values, because this is just y, and we are adding 4, and that's going to make us shift up 4. And so you can take every point that you got when you graphed this, shift them all up 4, and then you will have this new line, this shifted function. There we go. And this would be f of x plus 4, all the y values with 4 added onto them. Okay, and that would be our function. G of x over here is similar, since the first one was this line right here, and now we want minus 3. That means we are going to be shifting sideways, but with the opposite sign we're going to be shifting forward 3. And so I will just take each of the points that I got when I graphed g of x, I will move them each over 3 in the positive direction, and then I will connect those. And this will give me g of x minus 3. Now the reason it comes out minus instead of plus is this. When I attempt to plug in 3 to this equation, the first thing that happens is the x is transformed, and when I put in 3, I'm getting 3 minus 3 is 0, and so the actual value I will get out is the value I would have got if I plugged in 0 to this, and so there it is. When I plugged in 4, 4 minus 3 is 1, the actual value I plug into g is 1, and so then I got 2 minus 1, or 1, this value right there. And so every value we plug in for x actually acts like a value that's 3 smaller than it, and that's why this graph ends up shifting. So you'll need a bigger value to get that same graph. On worksheet 2, you'll see a whole section on shifts. And so on this, it says graph the functions and describe the transformation. And so my original function right here is a parabola, and it is shifted backwards 3, the opposite sign, and down 2. And so I started from here. Normally a parabola would just be at 0, 0 facing up, and I counted backwards 1, 2, 3, and down 1, 2, and I got that vertex. And then I proceeded to get the right width here. Now, students could plot points for this. That's what we've primarily done in the past, and that would be fine. They should be able to use symmetry. If they plotted this point, they could flip it over. If they plotted this point, they could flip it over, a line of symmetry. That would be a great way to do it. One of my students a few years ago came up with it. They noticed after plotting points several times that the first move was always the same as the number in front, this rate of change number. And so in this case it went up 1 over 1, but if you're starting with a 1, they noticed that it went up by odds, so up 1 over 1, then up 3 over 1, and then up 5 over 1. If we had the next one, it would be up 7 over 1. And that class really capitalized on that. That year that boy discovered it, that class capitalized on that a lot. They never wanted to really plot a table of values because they knew what that slope change was going to be. As a matter of fact, they even made up rules for if there was a number in front and what they did. And so however you choose to get these points, once you have that vertex, then you have this graph. The one thing I want to warn you about is with the task, it's relatively important to be pretty accurate. So you don't just want to generally draw something facing up, because you might need to actually exactly hit that point to achieve the prize. And so they will need to find a way to be very accurate with their graphs and not generally just have the right vertex and face up. So this is the graph of f of x. And now we want to do f of negative x. We're putting a negative inside, and we know that that reflects us across the y-axis. Every x we put in will act like it's opposite. So if I put in a negative 3, it will act like a positive 3. And so I have 1, 2, 3, negative 2. And so I'm going to go the other side, 1, 2, 3, negative 2. This point right here was negative 2, 1, and negative 1. And so I'm going to go positive 2, 1. And same with this point right here, positive 4, 1. And I'm at this point tempted to go up 3 over 1, up 5 over 1, because I know the width of the parabola did not change, and that's a great shortcut. And so this would be the graph of f of negative x. Okay. When it says describe the transformation, we are talking about transformation notation as they learned it in Math 2. And so on this particular problem, we would say f of x goes to f of negative x, and if f of x has a point xy, like this one right here, which happens to be negative 3, negative 2, then f of negative x will have the opposite sign, negative xy. Positive 3, negative 2. Same y, only the x will change signs. And so this is transformation notation. Now you have the option, if you would like, to let your students write this out in words, but it does get more complex as we go to do that and have multiple transformations going on. So I know in Algebra 2 we did a lot about left 3, down 5, or things like that. But they do need to be practicing this transformation notation that they learned. This is the notation that we've seen on the SBAC. It's not really the notation that's used in our Math 2 book, but it is the notation that we've seen on the SBAC, and so they had review worksheets and tests that were written with this notation interchangeably with the book notation. And you might find students who are more comfortable with that book notation that they had, and that would be okay, but I would start, since we're away from that, I would start favoring this notation because it's the one they're most likely to see on the SBAC this year. Or their junior year, whatever year they are. Here's one that asks how do you get from F to G. They need to make sure they're reading start at F, go to G. And so on this graph, I already graphed f of x and g of x. F of x was negative x squared, there it was. G of x was x plus 3 squared plus 5, so back 3, up 5, there it was. And now I wanted to describe that transformation. So in transformation notation, I would be going from f of x to g of x. And f of x is this guy, and if I make his points x, y, then g of x has a lot of things going on. G of x is a reflection, because it's facing up instead of down, and it's also a translation, where it has slid back 3 and up 5. And so you need all of those things to happen. Since the reflection is over the x-axis, the sign that is changing is the y sign. The y is changing from a -1 to a +1 if we reflect. And so what ends up happening is the x, we don't need to really worry about the negative. For the x, what has happened in each point? If this point originally had an x of 0, this point has an x of -3. All the x's just went back 3. But the y's had a couple different things happen to them. They reflected over, and then they also went up 5. And so this would be a way to write that transformation in transformation notation. Again, you're welcome to use words to describe that. We're going to probably need to review this more, though, throughout the year before they test in May. And this is a good opportunity, one of the very few opportunities we have during the course to review this. So it's a nice spot to be able to do that. Again, for them, it's something they've seen before. This is not a new thing. For you, if you haven't been teaching the Math 2 or some geometries with transformations in them recently, this might feel a little awkward, but remember, for the students, this is just, oh yeah, we did this last year, and they even did it in May, so it would not be that far long ago. Okay. Couple more, and then we're going to be done with this. Here we have ones from worksheet 3. Here's f of x graphed, here's negative f of x graphed, and they want the transformation from f of x to negative f of x. And so to do this, I kept all the x's the exact same, and the y's I multiplied by a negative. Negative f of x, remember, means negative y value. For number 8, I graphed g of x as it was. Now, because it says g of x minus 5, I know I'm going to be moving sideways 5, so each and every point I could count over 5, this one to this one, this one to this one, and I eventually will get this graph right here. And this is g of x minus 5. When it says label, that's what we're talking about, label which graph is which. And so to get from this graph to this graph, what we need is the x values to slide +5. So the x will be +5. The y value hasn't changed. They're still the exact same level on the y-axis, so the y is just 5. So that's some uses of shifts during the course of the chapter. And again, this is a key for the entire first semester. Thanks and good luck.